where curiosity gets cozy and the wild, ancient planet we live on becomes the perfect bedtime story. Tonight, we're taking a journey so deep into the past that even the rocks barely remember it. A time before trees, before oceans, before even the moon looked the way it does now. A time so old, so alien, it doesn't feel like Earth at all. We call it the Hadean Eon, named for Hades, the ancient Greek underworld, and not because it was particularly evil, but because if Earth had a version of its teenage years, this was more of a lava-flinging toddler tantrum. But what was it really like to stand, or rather float, because land as we know it barely existed, on a planet still becoming itself? Was there water? Was there air? Was there even a sky? And while we're at it, where in the world are you tonight? What time is it in your little corner of the planet? Fitting, isn't it, that we're about to talk about a time before clocks, before continents, before even the first breath of life, and yet here you are, nestled in this moment, listening from the far future of Earth. If you find this drift into deep time soothing, intriguing, or just a gentle companion for your evening unwind, I'd be ever so grateful if you gave the video a like or subscribed. It helps this quiet space reach others looking for a soft pause too. So settle in, slow your thoughts, and let's begin. Because before life could begin its long improbable story, before dinosaurs, trilobites, or even single-celled pioneers, there was fire, there was rock, there was silence. Roughly 4.5 billion years ago, Earth was born in violence, not with a whisper, but with a collision. A newborn world still warm with cosmic birth and immediately plunged into chaos. It was not a blue planet, it was red hot and raging, and yet, somehow, in the churning mess of magma and metal, the seeds of oceans, continents, and even life itself were quietly stirring. So how did something so harsh become the only known cradle of a life in the universe? That's what we're here to find out. Sometimes the most extraordinary revelations begin with a flicker in a compass. Not a grand explosion, not a fossilized skeleton, or a gleaming meteorite, but something quiet. A twitch in the needle, a slight hesitation. In the Canadian Shield, among some of the oldest, most stoic stones on Earth, a few geologists noticed something strange. They were studying ancient Zircon crystals, tiny, tough survivors embedded in much older rocks, when the compass they used for orientation didn't quite agree with what the textbook suggested. It was just a quirk, a moment. But the more they looked, the more the anomaly grew teeth. These zircons, discovered in the rugged terrain of Western Australia and the Jack Hills, weren't just old, they were impossibly old, over 4.3 billion years, some of them. Grains of minerals so tiny you could lose one in an eyelash, and yet inside each was a secret. Traces of an Earth that should not have existed yet. For a long time, the Hadean was thought of as a geological void, a black box of time. No rocks, no sediments, no record. It was as though the planet, fresh from its cosmic birth, had hit the reset button again and again, melting and remelting itself until nothing of its early chapters remained. But then came the zircons. These crystals are like nature's tiny time capsules. They form in the presence of water and granite, not the fire-forged basalt of volcanoes, but the slow, considered cooling of continental crust. To find them so early in Earth's timeline was like discovering a glass of iced tea in the heart of a volcano. Impossible, but there it was. Inside them, traces of oxygen isotopes hinted at something utterly unexpected. Liquid water, perhaps even oceans. At a time when we thought the planet was still wrapped in flame and fury, there may have been rainfall, rivers, a shy young sky learning to clear. Scientists like William Peck and Simon Wilde pored over these crystals with lasers and spectrometers, dissecting each one down to its atomic signature. And with every sample, the picture of the Hadean began to shift. It wasn't just fire and brimstone, it was something more subtle, more Earth-like. somewhere in those 500 million years between Earth's formation and the rise of the first true crust, the planet calmed down just enough, just briefly, for water to settle, for rocks to form, for zircons to grow like tiny sparks of clarity in a planet still thrashing through its infancy. It's strange to think that the story of Earth's earliest days might be found not in vast landscapes or deep ocean trenches, but in particles no bigger than a grain of sand. Yet these tiny fragments, sturdy, resistant, ancient, have become the most trusted witnesses to a world long gone, and they were discovered not with fanfare, but with patience, with careful measurements, endless field expeditions, and the kind of scientific curiosity that refuses to give up on lost time. To imagine the Hadean, we have to let go of almost everything we associate with the Earth we know. There were no trees swaying in the wind. There may not have been wind at all. The atmosphere, if it could be called that, was thick with carbon dioxide, methane, hydrogen sulfide, a brew so toxic and dense that sunlight filtered through it like amber through syrup. No blue sky, no birdsong, only the distant shimmer of molten rock, flowing across a surface still cracking and reforming like the skin of soup just beginning to cool. In fact, for a long while the sky itself may have glowed. After Earth's formation, it endured what scientists call the late heavy bombardment, a cosmic gauntlet of asteroids and comets that pummeled the planet for hundreds of millions of years. Some of these impacts were so intense, they would have vaporized oceans and stripped away atmosphere in moments. Whole regions of crust melted, turned back to magma, reflowed like wax under flame. And yet, somehow, something held on. There's a theory, still debated but hauntingly beautiful, that after one particularly enormous collision, a fragment of Earth was flung into space. That fragment coalesced, cooled, and became our moon. This event, known as the Giant Impact Hypothesis, suggests that a Mars-sized object, dubbed Theia, slammed into the young Earth with such force that both bodies partially liquefied. The debris, caught in gravity's embrace, gathered into a glowing disk, then slowly circled and clumped until it became the satellite we now know as Luna. If that's true, then every moonrise is a ghost story, a memory of the most violent day Earth ever experienced. But the impact did more than just create a moon. It may have tilted Earth's axis, giving us seasons. It may have stirred the molten core, helping generate the magnetic field that protects us from solar radiation. And in the aftermath, strange as it seems, the Earth began to stabilize. The ocean basins deepened. The first hints of land began to rise. Steam condensed into rain, and rain fell in torrents onto the still hot surface, carving and cooling, shaping and soothing. The rock began to remember. It's here that those precious zircon crystals may have taken form, not in a planet of endless fire, but in pockets of quiet, in the first granite outcrops, surrounded by proto-oceans and skies that for fleeting moments began to clear. So the Hadean wasn't just hellish, it was also hopeful, a time of contrast, of cataclysm and creation. And today, thanks to a handful of crystals, a few oddly behaving compasses, and a stubborn refusal to give up on the past, we can begin to reconstruct the unthinkable. We can trace the whispers of Earth's first rains. We can guess at the shape of continents long since devoured. We can imagine the weight of clouds pregnant with the first ever storms. And we can ask, in awe and humility, how could life, fragile, complex, water-loving life, ever hope to arise in a world like this? The answer, as we'll see, lies not in perfection, but in persistence. In the quiet resilience of a planet that kept trying, kept cooling, kept changing, until at last it became the Earth we call home. But before we look forward to life's improbable spark, we must look back once more, deeper, farther, through the lens of isotope ratios and the stories told in ancient rock. Because even in Earth's darkest chapter, there were patterns, there was motion, there was something beginning to stir beneath the chaos. And now that we've set the stage, we can start to see it. The ancient world is calling, and it's ready to tell its story. To imagine the Earth during the Hadean Eon is to try to remember a dream you never had. There were no trees yet to sway in the wind, and no wind to move them. There were no continents to speak of, no shorelines to stand on, no oceans as we know them, only vast steaming pools where sky and surface blurred together in mist. The land was not land. It was an argument between solid and molten, between forming and falling apart. The surface of Earth in these first hundreds of millions of years was in a constant state of upheaval. You wouldn't have found rolling hills or lazy rivers, but rather a violent landscape of magma plains, impact basins, volcanic ridges, and floating rafts of half-cooled crust. The young planet had just finished accreting, gathering material from the leftovers of the solar system's formation, and it hadn't yet figured out how to be stable. Picture a sky the colour of rust, hazy and thick with carbon dioxide, methane, hydrogen, sulfide. The atmosphere was heavy, oppressive, and yet, strange as it seems, it was already evolving. Gases were bubbling out from the molten rock below, what scientists call volcanic outgassing. And these gases, toxic though they may be, were the first whisperings of an atmosphere. Not one you'd want to breathe, mind you, unless you were made of rock and fire, but an atmosphere all the same. Temperatures on the surface would have been unbearable to us. Hundreds, perhaps thousands of degrees Celsius in some places. Lava fields stretched for miles, only to be wiped clean again by asteroid impacts. Molten rock bubbled, then cooled, then was shattered by the next violent encounter. It was a landscape always in motion, never settled. And yet, in the midst of all this chaos, there were signs of something new, differentiation. That's the word geologists use to describe the process by which Earth's internal layers began to sort themselves. Heavy metals like iron and nickel sank toward the centre, forming the core. Lighter materials, silicon, aluminum, oxygen, floated up to form the mantle and eventually the crust. Earth was no longer just a rock spinning in space. It was becoming a layered, dynamic system, a planet with structure, a planet with a future. With a metallic core came something crucial, a magnetic field. Perhaps weak and inconsistent at first, but slowly stabilizing. This magnetic shield would one day protect Earth's surface from the solar wind, a constant stream of charged particles from the sun. Without it, the early atmosphere may have been stripped away like wisps of fog. With it, the atmosphere could persist, clouds could form, rain could fall, and fall it did. Though Earth was blisteringly hot in its earliest moments, it didn't stay that way forever. Over millions of years, radioactive decay inside the planet, of elements like uranium and potassium, continued to produce heat, but the surface began to cool. Steam from outgassing condensed in the atmosphere, and eventually, after countless cycles of evaporation and collapse, it began to rain. Imagine it, the first rainfall on Earth. Not a drizzle, not a spring shower, but a torrent. It would have poured from the sky for centuries, even millennia. The ground, still hot, would hiss and spit as it tried to resist the water's advance. But the water persisted. Pools formed, lakes, oceans. In time, much of the Earth was covered in a global ocean, dark and deep and shrouded in mist. And here, at last, we reach a familiar image. Water, the great solvent, the birthplace of chemistry, and eventually of biology. But at this stage in the story, it was only the setting, not the actor. Beneath the waves, the planet continued to shift. The crust, thin and unstable, floated atop the mantle like cracked ice on a lava lake. Volcanoes erupted even underwater, releasing more gases, building up islands only to have them disappear again. In some places, proto-continents may have begun to form, granite outcroppings rich in silica, rising above the basalt plains, the beginnings of land, but they were small, ephemeral, more suggestion than structure. most of the surface remained ocean, and beneath it the dance of minerals had begun. Without life, the oceans were chemical soups, rich in iron and sulfur and other elements leached from the crust. The water was likely acidic in many regions. No coral reefs, no fish, no plankton blooms, just heat, pressure and chemistry. Still, this was enough. In places where volcanic activity met seawater, hydrothermal vents along the mid-ocean ridges, complex molecules began to form, not life, not yet, but building blocks, chains of carbon, primitive lipids, amino acids. These molecules were the alphabet. Life would be the sentence. And while this was happening, the surface was still being battered by space. The late heavy bombardment, that violent flurry of cosmic debris, may have lasted until about 3.8 billion years ago. Some believe it was even responsible for multiple extinction-level resets, boiling oceans and sterilizing the crust, only for Earth to start over again. But others suspect life may have been hiding by then, tucked into hydrothermal niches, protected from the chaos above. In either case, these constant impacts didn't just threaten life, they may have seeded it. Some meteorites contain organic molecules, some even the precursors to RNA. It's possible that the very ingredients of life came from space, hitching a ride on ice-rich comets or carbonaceous chondrites. Earth, still young and hungry, may have incorporated these gifts into its own messy recipe. So the ancient world of the Hadean was both a battlefield and a laboratory. It was dangerous, yes, but it was dynamic, changing, trying, failing, trying again. The surface boiled, cooled, cracked, melted, rained, and boiled again. It was a planet in a loop of refinement, and every cycle brought it closer to balance. We often picture this period as a kind of wasteland. But that does the Hadean a disservice. It was dramatic, certainly, but not dead. There was energy, there was complexity, there was a relentless push toward form, and that form ever so slowly began to resemble something we could call Earth. By around 4 billion years ago, stable crust may have formed in scattered patches. These weren't continents as we know them, but they were durable, granite-like plateaus that resisted erosion. Above them, the sky was clearing. The atmosphere, though still hostile, was thick enough to hold warmth. The oceans, while acidic and iron-rich, were deepening. And below the waves, complex chemistry was unfolding in secret. It's hard to say when life began, we simply don't know. The fossil record from this time is, understandably, sparse. Rock gets recycled, crushed, melted, disguised. But some of the oldest potential signs of life, carbon isotopes that may point to biological activity, come from rocks more than 3.8 billion years old. If those signs hold true, then life emerged not long after the worst of the bombardment ended. Not after the chaos, but within it. Life did not wait for Earth to be peaceful. It arrived while the ground was still warm and the sky still wept. It didn't ask for comfort. It asked for possibility. And the Hadean, against all odds, gave it that. This vision of early Earth comes not from one discovery, but from many. From geologists hiking into remote mountain ranges to chip away at ancient metamorphic beds. From chemists analysing isotope ratios in tiny crystals. From planetary scientists modelling the heat flow of a young molten world. From lunar studies that show the scars of shared violence. From Mars even. From meteorites that hint at similar beginnings on another planet. Together, these stories form a tapestry. Not a perfect picture, but a textured one. The Hadean wasn't static. It was a symphony of change. A rolling storm of geology and chemistry and celestial drama. It was the Earth we know, but only just starting to become itself. So when you picture that ancient world, don't just see fire, see transformation. See a sky clogged with sulfur and the first ghost of blue beyond it. See oceans churning with heat and potential. See islands of granite poking their heads above the waves, wondering if they'll last the decade, see lightning crackling over a sea of carbon-rich foam, see the first drop of rain sizzling on a newborn rock, see a world not ruined but rising. The ancient Earth wasn't waiting for life, it was becoming it. To understand how Earth changed, really changed, we need to return to a period of violence so complete it nearly wiped the planet clean. If the early Hadean was a wild painter's first furious brushstrokes, then this was the hand that scraped the canvas down to raw wood again. It's called the Late Heavy Bombardment, a phrase that sounds like an artillery campaign, and in some ways it was a cosmic one. For hundreds of millions of years after the planets formed, the solar system was still littered with debris, leftovers from the birth of the sun, from planetary collisions, from wayward wanderers nudged off course by gravitational tides. And all of it had unfinished business with Earth. What caused this deluge of impacts isn't entirely settled, but one leading theory is known as the Nice model, named, fittingly, after the city in France, not the adjective. In this model, the gas giants, Jupiter, Saturn, Uranus, Neptune, didn't form in their current positions. They migrated, they danced, they stirred the pot. As these massive planets drifted, their gravity reshuffled vast clouds of icy bodies and rocky fragments in the outer solar system, especially the Kuiper belt. Like a child upending a box of marbles, this migration sent a cascade of objects inward, crossing paths with Earth, Venus, Mars and Mercury. The result? Chaos. Some of these impactors were small, the size of a house, a hill, a mountain. Others were the size of cities, islands, or small continents. When they struck, they did not ask permission. Oceans boiled, atmospheres were torn asunder, entire regions of crust liquefied on impact. Shock waves circled the globe. The sky turned black, over and over again. It wasn't one event. It was a storm with no eye, a blizzard of stone and iron and ice. For a time, it may have rained fire more often than it rained water, and yet the planet endured. But here's where things get strange. Destructive as it was, the late heavy bombardment may not have been a step backward. It may have been the pressure Earth needed to evolve. Each impact shattered the surface but also injected energy into the system. Each crater cracked the crust, creating new pathways for magma to rise, for gases to escape, and critically, for water to seep into the deep earth and cycle back out again. In a sense, the bombardment may have kick-started plate tectonics, that slow, shuffling ballet of crustal plates that shapes continents, creates mountains, and keeps the planet geologically alive. Without tectonics, Earth might have ended up like Venus, a stagnant surface with no way to release internal heat. But with it, Earth began to breathe, to exhale, to move. It also stirred the ocean chemistry. Each impact vaporized rock and seawater, triggering shock reactions that could generate new minerals, release metal ions, and churn the deep ocean into a reactive, reducing environment. Conditions, in other words, rich with possibility. This churning, melting, cracking Earth became a kind of pressure cooker. Add water, heat, pressure, and carbon, and you don't just get magma, you get the foundations of biochemistry. Down near hydrothermal vents, those seafloor chimneys belching mineral-rich fluids into the ocean. The conditions were already strange. Temperatures in the hundreds of degrees Celsius, superheated water laced with sulfur, iron, hydrogen, a world of extremes, but also one of gradients. Temperature, pH, chemistry. And gradients are where energy flows, where life someday might spark. So even as the planet was being pummeled from above, it was preparing itself from below, laying down minerals like pyrite and olivine, cycling water through deep fractures, establishing redox environments where electrons could hop from molecule to molecule, the heartbeat of future metabolism. It's a strange kind of irony that destruction could make the conditions for creation. But Earth seems to favour paradox. In the worst violence came the best ingredients. In the chaos, a kind of symmetry. And while much of this is inferred from isotopes, simulations, and mineral traces, there are tantalizing clues that life didn't just wait for the storm to pass. It may have emerged right in the middle of it. Carbon isotopes in ancient rocks from Greenland, as old as 3.65 billion years, show a signature consistent with biological activity. Not proof, not fossils, but a whisper, a chance that life was already flickering when the sky was still falling. And if that's true, then life is not just tenacious, it's opportunistic. Still, we have to be careful. The record is sparse. The rocks have been heated, altered, bent by time. We're listening for voices through a broken radio, but the hints remain. Graphite grains with skewed carbon-12 ratios, layered structures that look suspiciously like stromatolites, microbial mats turned to stone, metamorphosed sediments that still bear scars of something biological. Whatever the case, something had changed. Whether life was already stirring, or whether the ingredients were just aligning, Earth was becoming something new. No longer just a boiling sphere of the rock and gas, but a system with cycles. The water cycle, the carbon cycle, the beginnings of a biosphere. And one of the most important elements in that transformation, both literally and narratively, was oxygen. Not the kind we breathe, not yet. That would come much later. But even trace amounts of oxygen can change everything. Some of the earliest zircons contain evidence that the Earth's surface may have had oxidizing conditions, at least locally. And some of the oldest rocks contain minerals that only form in the presence of water and a touch of oxygen. That touch may have come from photolysis, sunlight splitting water molecules in the upper atmosphere, or perhaps from the earliest photosynthetic microbes if they had already emerged. Either way, the presence of oxygen begins to close the circle, because oxygen isn't just a byproduct of life, it's also a fuel for change. With even small amounts in the atmosphere, new kinds of minerals can form, new weathering reactions can occur, iron in the ocean begins to rust, to settle, to create layers of banded iron formations, those beautiful red and black strata that still lie buried in ancient rock. And oxygen, once it begins to accumulate, can also protect. It contributes to the formation of ozone, that fragile, vital shield against ultraviolet radiation, a shield that would one day make the surface of Earth habitable for life beyond the oceans. But we are not there yet. In the Hadean, oxygen was still a whisper, not a voice. The atmosphere was thick with carbon dioxide laced with methane, a greenhouse world, but not a dead one. The oceans were acidic, but rich. The sky was dark, but clearing. The land was broken, but forming. And beneath it all, deep in the Earth's mantle, a new engine was running. The convection currents, heat rising and falling, had begun to organise the crust into plates. Not the complex mosaic we see today, but something simpler. A few scattered slabs moving slowly, colliding, subducting. Plate tectonics, not just geology, a planetary pulse. And it is here, in the middle of fire and stone, that Earth stopped being just a place and started being a process. Plate tectonics began almost invisibly, like a whisper beneath the crust. Nothing so dramatic as crashing continents or uplifted mountain chains, not yet. But in the deep mantle, where heat surged upward and denser rock sank down, the first great circulations had begun. The Earth was churning from within, and over time this subtle, silent dance would become the engine of continents, of oceans, and of life itself. You could think of it as Earth's heartbeat, a slow, pulsing rhythm that moves rock the way the tides move water. At the surface, it would have been nearly imperceptible, a rise here, a ripple there. But deep below, massive slabs of crust were beginning to buckle and fold, to dive beneath one another, to recycle. This recycling was no small thing. It was the beginning of a system capable of regulating its own temperature, its own atmosphere, even its chemistry. It was the start of a planetary thermostat, and without it, Earth would have long ago overheated or cooled to a frozen stillness. Instead, it adapted, slowly, relentlessly. With every new subduction zone came fresh magma. With every new ridge came fresh ocean crust. But to form stable land, true land, crust that could rise above the waves and persist for more than a moment, you need something more. You need felsic crust, rock rich in silica and aluminum, lighter than the dense basalt of the ocean floor. And to make felsic crust, you need both water and tectonics. Subduction draws water deep into the mantle, lowers the melting point of rock and allows granite to form, granite the great builder of continents. So somewhere around the end of the Hadean, a new kind of land began to appear. Not the jagged spires of future mountains, but low scattered islands, what geologists sometimes call cratons, ancient fragments of continental crust that have survived for billions of years. They are the bones of today's continents, the old hearts of the land we stand on. We walk on them every day and rarely think of them, but they remember a time before rivers, before roots, before breath. And while these early land masses were small, they mattered. Because land above water changes everything. It gives the planet new textures, new surfaces for rain to strike, to erode, to carry minerals back to the sea. It creates shallow coastal zones, rich with nutrients and energy gradients, the perfect stage for future biology to experiment. Even the act of erosion is transformative. When rain falls on bare rock, it begins the long, slow process of breaking it down, grain by grain. This isn't destruction, it's preparation. Weathered rock releases ions like calcium, potassium, magnesium. These dissolve into rivers, then into oceans, altering the chemistry of seawater, providing the very ingredients that cells, someday, will crave. This is Earth writing the recipe for life, one molecule at a time. And yet, as transformative as water was, another change loomed beneath the surface, one even more profound. It was a shift in energy, a subtle reorganization of planetary metabolism. Because at some point, likely in these warm, mineral-rich waters, chemistry gave rise to complexity, and complexity eventually gave rise to replication. Not life, not yet, but the flicker of it. Picture a bubble, a lipid vesicle, fatty acids aligning themselves into a tiny membrane, enclosing a bit of fluid. Inside, a handful of organic molecules, maybe amino acids, maybe nucleotides. Outside, a constantly changing environment, hot, cold, acidic, alkaline, full of metal ions, full of energy. Now imagine that this bubble grows, that it divides, that some of its contents begin to react, to self-organize, that a strand of RNA perhaps begins to copy itself, not perfectly, but well enough, and that among all these trials, a few versions survive better than others. That's not just chemistry anymore, that's evolution. And from that point onward, Earth would never be the same. The transition from non-life to life wasn't a single moment. It wasn't a spark, a bang, a divine breath. It was a spectrum, a cascade of tiny steps, some fast, some slow, many lost to time, but each one shaped by the environment the Hadean had built. The ocean stirred by tides and impact waves, the vents exhaling metal-rich fluids into the abyss, the rocks releasing phosphorus and iron and sulfur, the sky clearing ever so slightly, letting in light. And light, in time, would become food. The earliest life forms, if they existed then, may have been chemotrophs, feeding on chemical gradients, living in darkness. But eventually, perhaps by the dawn of the next eon, some tiny ancestor would harness photons, would learn to capture sunlight and store it in sugars, photosynthesis, and with it, the slow production of oxygen. But that's still far ahead. In the Hadean, the world is only just beginning to support that kind of complexity. Still, signs of the shift are written in ancient rock. Some minerals found in Hadean zircons appear only when certain temperatures and pressures are met. conditions that suggest continental crust was already thickening in places. Other isotopic ratios hint that water had not just arrived but endured, that oceans had been present for millions of years, stable enough for geochemical cycles to establish themselves. Even the moon, ever our silent companion, holds clues. Its surface is littered with craters that match the timeline of Earth's late heavy bombardment. Unlike Earth, the moon has no atmosphere, no weather, no plate tectonics to erase those scars, so its face is a record, a fossil sky. And when we studied the rocks brought back by Apollo missions, we found more than basalt and dust. We found a timeline, a shared history, a confirmation that Earth too was shaped by that same fiery storm. And yet, despite that storm, the Earth cooled. Despite the chaos, land rose. Despite the darkness, rain fell. Despite the heat, the ocean stayed. Despite everything, the conditions for life not only survived, they improved. If you step back and look at it, the Hadean Eon wasn't just the beginning, it was the crucible, a time when Earth was constantly balancing between ruin and resilience. And each time, resilience won. It's humbling to realise that our planet didn't start out hospitable. It earned that title through violence, through patience, through billions of experiments in rock and gas and water, and through the simplest, most powerful mechanism of all, time. No one built Earth to support life. Life emerged because Earth, against all odds, created the right patterns, right heat, right minerals, right tides, right rhythm. And perhaps that's what makes this story so quietly profound, because even before the first microbe blinked into being, the stage was being set with care, not by design but by interaction, by persistence, by natural consequences repeated enough times to resemble grace. When we look at the Hadean today, we no longer see a lifeless world. We see a world preparing for life. The ancient oceans were not sterile. They were rich with potential. The air, though toxic, was layered with ingredients. The land, though jagged and bare, was rising into form. And beneath it all, the engine of a planet turning itself inside out over and over, until something began to emerge from the deep. A spark, a cycle, a breath. The Earth does not change quietly. For every new step forward, it sends 1,000 ripples outward. And in the wake of the Hadean Eon's roaring furnace, the planet began to whisper, then murmur, then hum. A growing chorus of chain reactions, subtle and vast, immediate and slow. The world, once a boiling cauldron, was now something else entirely. Still hot in its heart, still volatile in its crust, but on the surface, change was setting in. And it came not as a single moment, but as a great unwinding. The kind you only notice if you watch with enough patience to count by aeons. After the final blows of the late heavy bombardment tapered off, like a storm reluctantly releasing its grip, Earth was left scarred but standing. The crust, once thin and fragile, was thickening in places. Continents, still small and scattered, had begun their long journey toward the forms we know. And beneath them, a slow-motion tug-of-war played out between cooling and convection, between stability and stir. But it was the oceans that responded first. The oceans had already endured the worst, evaporated in an instant by impacts, reformed by rainfall, darkened by ash, enriched by hydrothermal chemistry. Now, with the skies clearing ever so slightly, sunlight was beginning to reach their surface more consistently. This was no bright blue sky just yet, no gentle beam across a calm wave, but it was enough for energy to start feeding chemistry, enough for feedback loops to emerge. Earth for the first time began to react to itself. Rain fell on rocks, rocks weathered into ions, rivers carried those ions back to the sea, carbon dioxide dissolved in the water, forming carbonic acid. This too weathered the land. Every drop of rain became a miner, every stream a slow conveyor belt of planetary memory. And as CO2 levels in the atmosphere slowly dropped, pulled down by weathering and trapped in seafloor sediments, the temperature began to respond. The greenhouse blanket thinned. The Earth, still hot from within, began to cool at the surface. Not all at once, not evenly, but steadily. This was the beginning of climate regulation, a planetary scale homeostasis controlled not by life, not yet, but by rocks. It's called the carbonate-silicate cycle, and it's one of Earth's most powerful quiet systems. A negative feedback loop. The warmer it gets, the faster weathering pulls carbon from the sky. The cooler it gets, the slower that process becomes. Left alone, it's a thermostat that could run for billions of years. But it wouldn't be left alone for long, because in the oceans something new was stirring. We don't know exactly when life began, but let's imagine for a moment that somewhere in the deep sea near a hydrothermal vent, a bubble of lipids enclosed a strand of self-replicating molecules. That molecule made a copy, and the copy made a mistake, and the mistake, miraculously, improved the odds of surviving just a little longer. That's not the whole definition of life, but it's close enough for a first draft. If such organisms emerged, they would have faced a harsh world, acidic seas, heavy metals, UV radiation, and the occasional comet crashing into their home turf. But also energy gradients, mineral scaffolds, and raw chemical bounty. They didn't need oxygen. They didn't need sunlight. They needed opportunity. And over time, they found it. Early microbial life, if it survived, would have quickly started altering the very chemistry of the world around it. Not deliberately, of course, just as a byproduct of metabolism. The first cells may have been anaerobic chemotrophs, feeding on hydrogen or sulfur compounds, exhaling methane or hydrogen sulfide into the sea. And in doing so, they began to create niches, new chemical gradients, new waste products, new possibilities. Each reaction created a new environment, and each environment favoured different reactions. It was ecology before ecology had a name, a feedback loop made of cells, chemicals, and chance. And perhaps, in one quiet, shallow bay, where the sun just barely reached the sea floor, one of those microbes evolved a new trick. It found a way to use sunlight. This would be one of the most consequential changes in Earth's history. The earliest form of photosynthesis, probably not oxygen producing at first, involved using light to drive chemical reactions, an elegant shortcut. But soon enough, nature found a more powerful version, oxygenic photosynthesis, and that, as they say, changed everything. These tiny greenish microbes, ancestors of today's cyanobacteria, began releasing oxygen into the ocean as a waste product. Just a trace at first. The ocean absorbed it, like a sponge. Iron in the seawater grabbed it hungrily, oxidizing into rust and sinking to the bottom. This formed banded iron formations, those striped red and grey rocks we still find in ancient outcrops. They're the fingerprints of early oxygen, laid down layer by patient layer. But eventually the ocean sponge was full. There was nowhere left for the oxygen to go. So it began to rise into the atmosphere, not in a flood, not in a flash, but in a slow, steady seep. And this too triggered new reactions. Oxygen began to oxidize surface rocks, changing their colour, their chemistry. It reacted with methane, a powerful greenhouse gas, reducing its concentration and cooling the planet. It altered the kinds of minerals that could form. It began, in other words, to rewrite the rules, and in doing so, it set the stage for one of Earth's greatest paradoxes. The rise of oxygen may have triggered one of the planet's first major die-offs. Because while oxygen was a gift to the future, it was a poison to the past. Most of early life had evolved in a world without it. Oxygen for them was toxic. It damaged their proteins, interfered with their metabolism, destroyed the balance they had so painstakingly achieved. This moment is known as the Great Oxygenation Event, and though it would fully unfold in the next eon, its roots were already reaching deep during the Archean. And like all good Earth stories, it came with consequences. The atmosphere changed, the greenhouse effect weakened, the planet cooled, and eventually, some believe, It may have frozen. Not just a winter, not just a glaciation, a snowball. Evidence suggests that the Earth may have experienced periods of extreme glaciation, perhaps even reaching equatorial latitudes, ice from pole to pole, oceans covered in frost, a white Earth beneath a pale sun. And if life was to survive that, it would need to adapt again. Some clung to the warmth of hydrothermal vents. Some hid beneath the ice, in pockets of liquid. Some may have gone dormant, waiting for the thaw. But survive they did, and in doing so, they learned something new, that change was not the enemy, it was the environment. Meanwhile, above the ice, volcanic activity continued. Greenhouse gases still leaked from the mantle, and in time they built up. The ice melted, the planet breathed again. These cycles, freeze and thaw, bloom and bust, feast and famine, became a defining rhythm of Earth's young biosphere. Not stable, not safe, but dynamic, alive. And with each pulse the world grew more complex. As the planet thawed from its ancient slumber, the world stirred once more. It wasn't the first time, and it wouldn't be the last. But this thaw was different. It carried the fingerprints of oxygen, of cells, of light. Something in the fabric of Earth had changed. A threshold had been crossed. The oceans, once sealed under ice, opened to the sky again. Gas exchange resumed. Sunlight returned to the surface. Photosynthetic organisms, having clung to narrow refuges for untold millennia, bloomed across the seas like a tide of green mist. Their exhalations, oxygen, rose anew, and this time the atmosphere was more willing to accept it. With the planet's thermostat now being nudged by life itself, new balances began to emerge. Oxygen changed the rules of chemical interaction. It allowed for new kinds of respiration, more efficient, more energetic. Instead of scraping out a living through anaerobic fermentation, some microbes began to burn sugars cleanly, with oxygen as the flame. The result? A cascade of energy, far more than before. Life, once constrained by low-power metabolisms, suddenly had surplus energy to spend. And energy is a catalyst for complexity. Cells that once floated freely in the sea began to specialize. Some grew membranes to control their environment more precisely. Some developed internal compartments. Some even absorbed other cells entirely, forming symbiotic relationships that would one day give rise to mitochondria and chloroplasts. This was the beginning of eukaryotes, cells with nuclei, with organelles, with ambition. But we're still deep in the aftermath, in the long tail of consequences that the Hadean set into motion. The Earth hadn't just survived the bombardment, the oxygenation, the freezes, it had been transformed by them. Each catastrophe was a chisel, each recovery, a rehearsal. Meanwhile, the crust beneath our feet continued to shift and grind. Plate tectonics, now in full swing, rearranged the face of the planet over and over again. Continents collided, ocean basins opened and closed. Volcanoes belched out basaltic plains the size of countries. Mountain ranges lifted and were worn down like wrinkles smoothed from a linen sheet. These slow movements weren't just scenic, they were essential. When tectonic plates subduct beneath one another, they carry carbon and other elements back into the mantle. When they rise, they expose new rock to weathering, which pulls carbon back out of the atmosphere. These processes formed a long, slow carbon cycle. Not as fast as the breath of a forest, but just as vital. The biosphere and geosphere were no longer separate. They were now entangled. Life altered the land, speeding erosion, forming soils, shaping rivers. And land altered life, creating islands of isolation, microclimates, new challenges to adapt to. The atmosphere, once a hostile haze, had now become a delicate bubble of interaction, layered with gases not only shaped by Earth's chemistry, but also by the metabolism of its smallest inhabitants. Even the very colour of the planet was changing. Before oxygen, the oceans were likely green or even reddish, stained by dissolved iron. But as iron oxidized and settled out, the waters cleared. With enough oxygen, The sea may have taken on the deep blue we now know. The sky too changed. As methane levels fell and ozone began to form, the heavens shifted from a dull orange or grey into the pale blue we now associate with home. But beauty, as always, was just a byproduct. What mattered more was what these changes allowed. Clearer skies meant more UV protection. Oxygen-rich oceans meant new chemical pathways. Stable land masses meant the possibility, someday, of multicellular life venturing from water to rock. But all of that was still far ahead. Back in this ancient aftermath, the world was still ruled by microbes. They formed towering reefs of stromatolites, layered domes of mineral and mucus, built slowly by colonies of cyanobacteria. Some of these ancient structures still exist in Australia and the Bahamas, modern echoes of a 3.5 billion-year-old practice. They are monuments to slowness, to collective effort, to survival. Each layer of a stromatolite is a diary entry. We were here, we made oxygen, we endured. And with every year that passed, with every layer laid down, the oxygen crept higher, into the sky, into the rocks, into the future. But Earth was not done reshaping itself. Not by a long shot. With every tectonic jolt, a new era of volcanism might begin. Some eruptions were small, lava gently pouring across the land. Others were catastrophic, large igneous provinces where magma flooded the surface for hundreds of thousands of years. These events could dramatically shift climate, releasing carbon dioxide, triggering warming, or in other cases releasing sulfur aerosols that cooled the earth and dimmed the sun. In both directions, life had to adjust, and often it didn't. Many of the earliest extinction events, long before animals existed to record them, were microbial. Whole branches of bacteria may have been wiped out by oxygen. Others suffocated in glaciations. Some simply ran out of food when their chemical niche disappeared. But with each collapse came a vacancy, and with each vacancy, evolution tried something new. This cycle, expansion, collapse, innovation, would become a theme of Earth's entire biological history. Not a ladder, but a pulse, a heartbeat. And through it all, time stretched on. The scars of bombardment slowly faded, eroded by water, buried by sediment. The moon, still circling overhead, grew more distant with each passing century. Its gravitational pull continued to stir the oceans, driving tides that may have helped early cells concentrate, mix, divide. Even now, the moon drifts away from us at a rate of about 4 centimeters per year. A slow farewell. But in those early days, it was closer, brighter, its tidal forces stronger. Some scientists believe these strong tides may have created shallow intertidal zones, where wet and dry cycles encourage the assembly of complex molecules. These are the quiet interactions we often forget. The moon and the ocean, the rock and the rain, the chemistry of sunlight hitting a tide pool, the wind stirring particles in a volcanic plume. All of it mattered, all of it connected. And somewhere, in this theatre of collisions and storms and slow recoveries, Earth's identity began to settle. It was no longer just a young planet, no longer just a lucky rock. It had become something else, a biosphere. Not just a place that hosts life, a place shaped by it. And that, perhaps, is the most beautiful consequence of all. Because when the chain reactions finally slowed, when the temperature stabilized, when the skies cleared, when the oxygen reached a threshold, what emerged was not a perfect world, but a living one. Messy, reactive, experimental, adaptive, capable of healing, capable of learning. A world where life didn't merely exist on top of geology like moss on a stone. It became the stone. It altered the climate, the rivers, the rocks, the atmosphere. It wrote itself into every system. It became inseparable from the story of the planet itself. And that, in the end, is the immediate aftermath of the Hadean. Not calm, not peace, but participation. The joining of all things, magma and microbes, sky and sediment, water and wonder, into a single evolving whole, a world that no longer simply spun, a world that began to dream. To understand just how miraculous the Hadean story is, we have to step back, far back, beyond oceans, beyond rocks, beyond Earth itself. Because Earth's early violence wasn't random. It wasn't just bad luck. It was part of a deeper rhythm, a pattern older than the planet, older even than the sun. A pattern written in stardust. Everything we are, everything this world became, was forged in stars. The iron in your blood, the calcium in your bones, the silicon in the sand, the carbon in every breath you exhale. These elements were born in the hearts of massive stars, fused in nuclear fire and cast into the galaxy when those stars died. Some exploded in supernovae, others collapsed into black holes, releasing shockwaves that seeded future clouds of matter. Our solar system, and every molecule in it, is a second-hand inheritance, a recycled masterpiece. Earth formed not from nothing, but from the ashes of 1,000,000 suns. So when Earth was born, it already carried memory. Not memory the way we know it, not thoughts or feelings, but atomic memory. Fingerprints of ancient events, isotopes that still hum with decay, echoing the violence of stellar deaths billions of years ago. Even now, radioactive decay from uranium, thorium and potassium provides heat from Earth's core. We stay geologically alive thanks to energy from stars that died long before our sun even blinked awake. This is the context in which the Hadean unfolded, not an isolated chaos, but a continuation of cosmic history. Even the moon, so crucial to tides, stability, and maybe even the origin of life, was likely born from a collision that itself mirrored countless other impacts throughout the universe. Planets and moons form through violence. They find balance only later. In fact, if we compare Earth's story to those of other planets, we start to see something strange. Earth is an exception. A miracle, not because it exists, but because it endured. Venus, our sister world, may once have had oceans too, but now it's a hellscape of sulfuric skies and surface temperatures hot enough to melt lead. Mars, smaller and colder, shows signs of ancient rivers and lakes, but it lost its magnetic field and most of its atmosphere, becoming a frozen desert. Why not Earth? Why did this world of all the rocky planets remain habitable? Not for a moment, but for billions of years. The answer may lie in cycles. Earth doesn't avoid catastrophe, it absorbs it. It bends, then recovers. The Hadean wasn't a glitch, it was the start of that cycle. Impact, collapse, adaptation, volcanism, cooling, oxygenation, freeze, thaw, diversification, over and over again. And if we zoom in, we find that even within the Hadean's chaos, there are echoes of previous evolutionary rhythms, not biological yet, but chemical. Consider the idea of chemical evolution, a prelude to life itself. Before cells, before membranes, before enzymes, there were molecules, and those molecules too followed patterns. Some formed more easily than others, some persisted longer, some reacted with sunlight or heat or minerals, and some, against all odds, began to self-organize. On the early Earth, in hydrothermal vents, in tidal pools, in clouds of volcanic vapor. Complex organic compounds were constantly being formed and destroyed. RNA precursors, lipids, sugars. All of them arising not from biology, but from chemistry, shaped by the planet's temperature, pressure, pH, and mineral scaffolding. In this view, life isn't a lightning bolt moment. It's a gradient, a slope, a slide from chaos into pattern. The Hadean wasn't a barren gap. It was the crucible in which complexity simmered, reduced, recombined, until one day something persisted. And here we find another kind of nested storytelling. The molecular reflects the planetary, just as the planetary reflects the cosmic. The Earth's crust differentiated just as molecules did. The atmosphere evolved just as protocells may have. Everything in its own way was becoming more ordered, not because of intention, but because of interaction. It's almost musical, the way these cycles nested into one another. The long cooling of the crust echoed the short-lived cooling of lava flows. The atmospheric shifts echoed the chemical changes in each puddle, each droplet. The tides mirrored the rise and fall of hot-cold chemistry, and together, this overlapping orchestra produced conditions ripe for something utterly new. But these weren't the first patterns Earth inherited. Even the solar system carries its own long memory. The asteroid belts, the orbital resonances of Jupiter and Saturn, the eccentric tilt of Uranus. All of these gravitational fingerprints play into Earth's story, modulating impacts, controlling orbital stability, influencing climate over millions of years. And beyond our solar system, other stars are surrounded by their own disks of dust and rock, their own early bombardments. We've observed them with telescopes. We've seen young stars lighting up like beacons, their protoplanets colliding in bright flares of infrared heat. Other Earths are forming even now in the dark, but will they survive what we did? Will their Hadeans last long enough to cool? Will their early chemistry find shelter in oceans? Will their collisions build moons? We don't know. But what we do know is that Earth had every reason not to make it, and yet it did. It didn't escape destruction. It danced with it. And this resilience wasn't a one-time event. Throughout Earth's deep time, there would be other apocalypses, 5 mass extinctions and perhaps more. Each one would wipe out vast swathes of life. Each one would reshape the planet's biosphere, and each one would be followed by recovery, diversification, innovation. It's a rhythm that began in the Hadean, a rhythm the Earth never forgot. And if we listen closely, we can begin to hear it, not just in rocks or isotopes or magnetic fields, but in the very structure of how the Earth operates, a memory etched into its behaviour, a long, looping song of endings and beginnings. This is what makes the Hadean so much more than a chapter in history. It's the overture, the underlying tempo, the reason the story could continue. Because if the Hadean had gone just slightly differently, if the moon hadn't formed, if the impacts were just a bit more extreme, if the water had never condensed, if the atmosphere had blown away, we wouldn't be here. There would be no story to tell, no breath to describe it, no eyes to look back across the ages and say, once the Earth was molten and now it dreams. The Earth has always been a creature of memory, not memory like ours, not thoughts or stories or dreams, but geological memory, deep memory, layered, pressed into stone, a kind of remembering that takes place without anyone needing to be there. And that memory is recursive. It repeats itself. Because the story of the Hadean didn't end when the crust cooled or when the moon settled into orbit. It echoed forward, into every tectonic shift, every volcanic eruption, every moment where the planet seemed to teeter between life and loss. The same processes that defined Earth's infancy are still shaping it now. The same internal heat, born from ancient radioactive elements, still drives mantle convection, still pushes continents apart, still builds mountains and carves ocean trenches. The same magnetic field, born of iron flowing in the core, still shields us from solar wind. The same cycles of carbon, born of silicate rock and acid rain, still tug at the climate, keeping Earth just warm enough for life to persist. And just as the Hadean mirrored cosmic violence, just as it carried echoes of stellar births and deaths, so too does every later mass extinction carry the echo of that first great upheaval. Because mass extinction isn't new. The Great Dying, the Permian event, 252 million years ago, caused by flood basalts, CO2 and runaway warming. The Cretaceous, 66 million years ago, caused by an asteroid impact, perhaps not unlike those that pummeled Earth in the Hadean. The Cryogenian glaciations, Snowball Earth. moments when the world froze almost completely, just as it may have begun to do under oxygen's first rise. All of these moments, these apparent collapses, are not accidents. They are part of the pattern. Earth grows through destruction. It transforms by letting go. It's as if the planet periodically resets the canvas, not erasing everything, but clearing enough space for something unexpected to emerge. And each time, life responds. Each time, life doesn't simply return, it transforms, becomes stranger, more resilient, more interwoven with the planet itself. This recursive structure is everywhere in nature, in tree rings, in the layers of a coral reef, in the slow, rhythmic advance of glaciers, in the winding helix of DNA, coiled and uncoiled with every cell division. Even evolution itself is recursive. Genes copied, mutated, tested, repeated. Species diverging, disappearing, diverging again. In that sense, life didn't just emerge from the Hadean, it inherited its habits. It became an agent of cycles. And if we think of Earth not as a backdrop for life, but as a participant in it, then the planet's very surface becomes a living document, a palimpsest. Stories written over stories, each layer containing the ghosts of those below. The continents we walk today are built on the bones of ancient cratons, fragments of Hadean crust. They have been buried, melted, folded, raised again. The air we breathe contains atoms once exhaled by cyanobacteria over 3 billion years ago. The water in your glass may have rained on basalt plains before the first cell divided. Nothing is lost, only changed. Even the very shape of time on Earth, deep time, is a gift from these ancient cycles. We don't measure time here in minutes or hours. We measure it in eons, in unconformities in rock, in the half-lives of uranium, in isotope ratios that can tell us whether the ocean was hot or cold, acidic or alkaline, salty or fresh, 4 billion years ago. And even now, with all our instruments, our satellites, our data, we still rely on the silent memory of minerals. Zircon still remains our most reliable timekeeper. Those little crystals, formed in molten rock, cooled in Earth's early crust, are like tiny hard drives, storing trace amounts of uranium and lead. From them we can measure the age of continents. From them we can see the first hints of water, the first signs of recycling, the first whispers of habitability. It's humbling to realise how much we owe to rocks, because rocks, unlike us, do not forget, and they show us that the events of the Hadean were not isolated. They were echoes of other echoes, nested inside even larger stories. Think of the planets around other stars. Thousands have been discovered. Some are rocky, some orbit in habitable zones, some may be Earth-like in mass or temperature. But we don't yet know if any of them carry the same scars, the signs of oceans, of plate tectonics, of magnetic shielding, of moons large enough to stabilize a tilt. What makes Earth special is not just that it's habitable, it's that it has been for so long. Habitability isn't a setting, it's a balance. Delicate, dynamic, and earned. And Earth, somehow, has held that balance for billions of years. In large part because of what it went through during the Hadean. Because when you've survived collisions with Mars-sized objects, when you've formed a moon and still managed to hang on to oceans, when you've been battered by meteors for 600 million years and still built a biosphere, you don't forget how to adapt. The Hadean, then, wasn't just a beginning. It was a training ground, a boot camp for resilience. It set the bar for what Earth could survive, and Earth has been clearing that bar ever since. Even now, when we speak of climate change, of ecosystem collapse, of tipping points, we are invoking cycles that stretch back billions of years. Not because the planet will be fine no matter what, but because we know what it takes to make change last. We know what it looks like when systems break, and we know what it costs to recover. This is the lesson nested inside all the others, that Earth has always been fragile, and it has always been fierce. It can freeze, it can burn, It can bury its memories beneath lava and ice, but it can also grow forests from volcanic ash. It can fill barren oceans with life. It can take the violence of its birth and turn it into music. Every sunrise is a coda to that original symphony. Every tide is a memory of lunar dance. Every breath we take, every carbon atom exchanged in leaf or lung, is part of a chain reaction started when rain first touched molten rock. We live in aftermaths, beautiful, improbable aftermaths. And if there's one truth the Hadean teaches us, it's this: that catastrophe and creation are not opposites. They are partners in time, each one making space for the other, each one shaping a world that somehow, even now, still manages to feel like home. It's easy to imagine Earth's story unfolding in solitude, to picture the Hadean, the Archean, the great cycles of geology and chemistry playing out in darkness, unobserved, unrecorded, unknown. For billions of years this was true, but eventually, much, much later, someone looked at a rock and asked, "How old are you?" And Earth answered very slowly. The earliest people to study the land weren't geologists. They were farmers, builders, wanderers. They read the landscape not through science but through survival. A ridge meant shelter, a cave meant safety, a stone shaped just right meant a tool. Over time, those stones began to hold more than function. They held mystery. Mountains became sacred. Springs became divine. The earth was alive, perhaps even conscious. And in a way, those instincts weren't wrong. But it wasn't until the last few centuries, a blink of an eye in planetary time, that we began to ask deeper questions. Not just what is this rock, but how did it come to be? One of the first great leaps came with James Hutton in the late 1700s, a Scottish farmer and thinker who looked at tilted rock layers and realised something astonishing. That these stones had once been horizontal, that time and pressure had tilted them, and that immense ages must have passed for this to happen. He wrote, "We find no vestige of a beginning, no prospect of an end." It was one of the first articulations of deep time, not years, not centuries, but eons. Enough time to turn oceans into mountains, enough time to forget the shape of the world and remember it again. From there, a cascade of discoveries began. Charles Lyell expanded Hutton's ideas into the field of uniformitarianism, the concept that Earth changes slowly, through ongoing processes we can observe today. Darwin, influenced by Lyell, applied that idea to life itself. Evolution was just geology made biological, slow, continuous, relentless. But the Hadean, that was still a mystery. For a long time we didn't even know it existed. The oldest rocks we could find were already complex, already altered. The earliest part of Earth's story seemed erased. And then came the zircons. Tiny, hard, beautiful. Found in ancient sandstones in Australia's Jack Hills, these little crystals, some no bigger than a grain of sand, held within them trace amounts of uranium. And uranium, over time, decays into lead at a very predictable rate. By measuring the ratios of uranium to lead in a single zircon, scientists could tell exactly how old it was. Not roughly. Exactly. And what they found astonished them. Some of these zircons were 4.4 billion years old. Older than any rock. Older than the moon, depending on how you measure. Older than we thought Earth could even be solid. The lead scientist on the project, John Valley, spent years analysing these crystals. With advanced instruments, ion microprobes, mass spectrometers, he and his team teased out their secrets, atom by atom. And what they found wasn't just age. Some zircons contained oxygen isotope ratios that suggested interaction with liquid water. In other words, these tiny gems were born in a world with oceans. Oceans that must have existed over 4.3 billion years ago. It shattered our assumptions. We'd imagined the early Earth as a lava ocean, a fireball, an endless hell. And in some ways it was. But not entirely. Not always. These zircons said otherwise. They whispered of rain, of crust, of quiet. It wasn't just Valley's work. Other scientists began finding similar clues in different corners of the world, in ancient Canadian cratons, in Greenland's Isua belt. In the oldest sediments, the most remote shields, fragments of Earth's first steps were surfacing, and with every discovery came new questions. Where was the first crust? How stable was it? Could life have emerged this early? One name that often appears is Stephen Modgis, a geologist who pushed the boundary of life's possible beginning back further than most dared. He studied isotopes in ancient rocks and suggested that life may have existed as early as 3.8 billion years ago, possibly even during the tail end of the late heavy bombardment. To many, it seemed unthinkable. How could life survive under constant bombardment from space? But Modgis and others pointed to the deep sea, to hydrothermal vents, to the relative safety of the subsurface. Maybe life didn't survive despite the chaos. Maybe it arose because of it. These weren't just theories, they were quests. Scientists hiked into uninhabitable terrain. They slept in tents, chipped at billion-year-old rock faces, carried samples across glaciers. They endured frostbite, exhaustion, isolation. Not for fame, not even for certainty, but because they felt that old, familiar pull, the desire to understand something ancient, something vast. And slowly the picture came into focus. Earth's early history wasn't blank. It was written in a language we had only just begun to learn, a language of isotopes, of trace elements, of inclusion zones inside zircons, a language of detritus and decay and incredibly patient deduction. Even now, every new sample brings some unexpected twist. A pocket of ancient water found deep inside a South African mine, perhaps unchanged for 1 billion years. A weird ratio of noble gases in a volcanic vent, hinting at primordial material still trapped in Earth's mantle. A magnetic signature in an ancient rock, suggesting that Earth had a magnetic field far earlier than we believed, shielding the surface from solar wind even when the sun was young and violent. Each of these clues feels small, almost inconsequential on their own. But together, they form a pattern. And slowly, we've begun to trace the contours of that first eon, not through fossils, not through myth, but through the quiet, patient labour of people who believed the Earth was telling the truth and simply needed help being heard. For the scientists who study the Hadean, discovery doesn't come in flashes. There are no eureka moments lit by candlelight or chalkboard triumphs beneath portraits of Newton. It comes slowly, with calibration, with doubt, with entire weeks spent staring at spectra, only to discover that what you thought was a signal was just background noise. But sometimes, if you're patient, the rock speaks back. Geologist Harrison Schmitt once called Earth's early record the tale told by a reluctant witness. Not a liar, but a planet who suffered something so old, so foundational, it forgot how to tell the story directly. Instead, it left artifacts, clues, partial sentences frozen in minerals. To read them, scientists have had to invent languages of their own. There's mass spectrometry, the art of weighing atoms. This lets researchers read isotope ratios with such precision that they can tell the difference between a rock that cooled 4.28 billion years ago and one that cooled 4.29. An eye that sees not in shapes or colour, but in time itself. There's laser ablation, ICP-MS, where lasers vaporize tiny spots on ancient minerals, letting scientists measure compositions without destroying the sample. A tool as surgical as it is devastating. There's nanosims, atom probe tomography, and electron microprobes, each pushing further into the atomic heart of things, peeling back layers that have not seen daylight since the moon was young. But perhaps the most powerful tool of all is restraint, because the oldest rocks, the real ones, the ones with true whispers of the Hadean, are few, scattered, and often altered. They've been reheated, compressed, stretched, folded, weathered. They don't give answers easily. and so every interpretation must be cautious. Every paper filled with caveats, every claim approached like walking on ice. Still, the story grows. Some researchers have suggested that the late heavy bombardment may not have been a single burst of chaos, but a more drawn-out drizzle of impacts. Others argue the very event may not have happened at all, that it's an illusion caused by sampling bias on the moon. The debate plays out not in headlines, but in quietly disputed conference talks, in careful edits between collaborators, in footnotes. And then there are those who wonder, could Earth have supported life even before the moon-forming impact? A wild idea. Unlikely, but worth asking. Because asking is what scientists do best. There's Elizabeth Bell, whose work with ancient zircons helped pin down those early interactions with water. Craig O'Neill, who runs models of early Earth tectonics, trying to guess how the crust first thickened. Linda Elkins-Tanton, who models magma oceans and planetary differentiation, the sorting of heavy metals into cores, light silicates into crusts. Each of them, in their own way, is asking, what happened in those first few 100 million years? And what does it mean that we're even able to ask? Because what really binds these researchers together are more than fieldwork or instruments or grants, is awe. Awe at the age of the materials they study, or at the fragility of evidence that somehow survived 4 billion years, or that human minds, finite, forgetful, so new, can trace a chain of reasoning that stretches back to a time when the world itself was almost liquid. And perhaps most remarkable of all, they do it knowing the story is incomplete, will always be incomplete. We may never find a true Hadean rock, untouched and perfect. We may never see the moment when chemistry turned into biology. We may never know whether the early Earth was grey or red or black or blue. But we try. We go to the Canadian Shield, the Acasta Gneiss, the Nuvuagituk Greenstone Belt. We slice samples thinner than paper and stare at them for weeks. We run computer simulations of molten planets and imagine oceans forming from vapour. We climb into submersibles and study hydrothermal vents, imagining what their ancestors might have looked like 4 billion years ago. We reach back, not because we expect answers, but because the questions matter. In the end, studying the Hadean is an act of humility. The further back we look, the more we realise how little we know, not just about Earth, but about emergence itself, how structure arises from chaos, how form arises from force, how something begins when it could just as easily have never begun at all. And still, every new zircon is a miracle, every isotope a map, every crater a clue. When you read the scientific papers, the real ones, dry and technical, you can still hear the wonder beneath the equations. A sentence describing a preserved D18O anomaly in zircon is, in its own way, a poem. It means, this rock touched water 4.3 billion years ago. It means, there was rain, and maybe rivers, when the world was still half magma. And sometimes, the people writing these papers will slip. A line will break from the scientific voice and become something more personal. They'll call a result surprising, a zircon remarkable, a signal beautiful. Because it is. All of it is. Earth is not just an object of study, it is a story. And the people who tell it are as much a part of that story as the rocks themselves. Their hands hold samples pulled from cratons older than multicellular life. Their minds hold timelines longer than myth. They aren't prophets, they aren't sages, just curious, persistent people asking impossible questions. And every now and then Earth answers back, softly, slowly, with a crystal, with a ratio, with a silence broken by inference. We live in a time when we can touch the deep past with data, when we can scan the structure of a single atom and feel the weight of an entire eon. It's almost too much to hold. But we hold it anyway, because in some quiet way, these stories, these zircon narratives, these isotope lullabies, these cratered timelines, remind us of something deeper, that the Earth is not just old, it is knowably old, that we can live in a world made long before us and still understand its shape, that we can write stories about things no eye has seen, no breath has touched, no mind has imagined, and still, somehow, get close to the truth. Not perfectly, not completely, but close enough to feel the heat, close enough to taste the water, close enough to remember something we never lived, and still carry inside us. Let's begin with something small, a single zircon crystal, just a few hundred microns across. You could hold it between 2 fingers and barely feel a weight. But within that tiny shard of time lies a kind of archive, not of fossils or bones, but of temperature, pressure, and memory. A library written in atoms. This is where deep science begins, not with vast theories, but with tiny certainties, measurable things, things you can weigh, things that radiate. Because the early Earth, unlike today, was radioactive, not in a cinematic, glowing green sense, but in the slow, invisible heartbeat of unstable atoms. Uranium, thorium, potassium-40. These elements decay at known rates, their nuclei ticking like ancient clocks, emitting particles that transmute them into something else: lead, argon, calcium. By measuring how much of each element remains in a mineral, geologists can calculate how long it has been decaying. It's called radiometric dating, and it's how we know that some zircons in Australia are over 4.4 billion years old. The method is careful, precise, often frustrating. A single inclusion, a flaw, a crack, a secondary event can throw off the numbers. But when it works, it gives us something almost miraculous, a timestamp from a world that no longer exists. These crystals form in molten rock, magma, then cool slowly, capturing elements from their environment like a snowflake freezing around specks of dust. Once locked in, the decay begins, time begins, and so we trace the ratios: uranium-238 to lead-206, uranium-235 to lead-207, each with its own half-life, its own rhythm. By comparing them, we can not only date the crystal, but often infer the environment in which it formed. Was it hot, wet? Was the magma rich in silica? Was the crust thick or thin? It's detective work, done with lasers and mass spectrometers, done with spreadsheets and patience, and from it emerges a surprisingly vivid picture of early Earth. For example, oxygen isotopes. By analysing the ratio of oxygen-18 to oxygen-16 in zircon, scientists can infer the presence of water. Oxygen-18 is heavier and tends to concentrate in cooler, water-rich environments. So a zircon with high O18 levels likely formed in the presence of liquid water, meaning the Earth had oceans, or at least rain, at the time. This is how we know Earth was already cool enough for water within 100 million years of forming. Then there's hafnium. Hafnium isotopes in zircon can tell us about the source material of the magma, whether it came from a freshly differentiated mantle or from older recycled crust. This tells us when continental crust first began to form, a key milestone in making Earth habitable. Some studies suggest this may have started as early as 4.4 billion years ago. Others push it later. The debate continues, one zircon at a time. These aren't just numbers, they're narrative points. Each isotope is a verb in the sentence of Earth's formation. Each ratio is a pause, a clue, a whisper. And this same attention to chemistry extends beyond crystals. Let's talk about mantle dynamics, the movement of rock beneath the crust. Even in the Hadean, Earth had a convecting mantle, a layer of solid rock that behaves like a fluid over long timescales. Hot rock rises, cooler rock sinks. This drives plate tectonics today, and may have done so back then. But how do we know? We use geochemical signatures, specific patterns in volcanic rocks that reflect their origin. Rocks that come from deeper in the mantle carry different trace elements than those from shallower depths. By analysing ancient rocks and comparing their compositions, we can model the structure and behaviour of the early mantle. There's also xenon isotopes in volcanic gases, telling us about the composition of the primordial atmosphere. There's neodymium and samarium, used to trace crust formation. There's carbon isotopes, which can even hint at biological activity if they show a preference for lighter carbon, a signature of organic metabolism. And then there's the big question. When did plate tectonics begin? Some scientists believe it started early as the Hadean, based on evidence of crustal recycling and early granite formation. Others argue for a later start in the Archean or even Proterozoic. The question hinges on multiple lines of evidence: thermomechanical models, rock stress patterns, isotopic ratios. It also depends on how we define tectonics. Was it global, like today, with rigid plates moving atop the mantle? Or was it a more chaotic, localised form, stagnant lid tectonics, where sections of crust occasionally sink but don't yet behave as coherent plates? To test these models, scientists use numerical simulations. These are computer models of early Earth, running equations that govern heat flow, density, pressure, and viscosity. By tweaking variables, core temperature, water content, radioactive heating, they can see which conditions lead to plate-like behaviour. And what they find is fascinating. Water plays a critical role. Even a small amount of water in the mantle lowers the melting point of rock, softens the crust, and allows subduction to begin. Without water, plate tectonics may never have started. Without tectonics, Earth may have resembled Venus, static, volcanic, uninhabitable. Water, again, becomes the hinge. Geoscientists also study magnetic minerals, like magnetite, to infer when Earth's geodynamo first kicked in. This is the swirling of liquid iron in the outer core, generating a magnetic field that protects the atmosphere from solar wind. Without it, radiation would have stripped away the oceans long ago. We'd be Mars. Tiny magnetic signals in ancient rocks, sometimes less than a billionth of a Tesla, can tell us whether Earth had a magnetic field and how strong it was. Some suggest it started by 3.5 billion years ago. Others push it back further, and then we have the deep connection between Earth and its moon. Thanks to lunar samples, especially those returned from Apollo missions, we know the moon has its own isotope ratios, its own record of impacts, its own thermal history. When we compare those to Earth's, we find uncanny similarities, enough to support the giant impact hypothesis, that a Mars-sized body struck Earth, ejecting material that coalesced into the moon. Computer models have refined this idea, showing how such an impact could create a debris disk that forms a satellite, while also heating Earth's mantle and setting the stage for crust formation. It may have also reset Earth's atmosphere, blowing away the original hydrogen-rich envelope and allowing a new secondary atmosphere to form from volcanic outgassing. This atmosphere, rich in CO2, nitrogen, and water vapour, created the conditions for cooling, rain, and oceans. In other words, the moon-forming impact wasn't just an accident, it was a chemical pivot, a thermodynamic reboot. Even the late heavy bombardment, if it occurred, may have been part of this story, a consequence of shifting orbital resonances between Jupiter and Saturn that destabilised the outer solar system. A single planetary hiccup echoing through time as a storm of asteroids, and Earth endured. We know all this, not because we were there, not because we imagined it, but because the rocks remember, because isotopes don't lie, because chemistry, when read correctly, becomes history. And even now the story continues to refine itself. Every time a new analytical technique is invented, every time a lab sharpens its resolution, we open one more layer of the archive, and Earth, once more, speaks. To understand life's origin, you have to forget almost everything you know about life. Not plants, not animals, not even cells. You have to go back to a world without shape, without replication, without DNA. A world not yet alive, but rich with potential. A world in which chemistry was the only force in motion, and order was something that emerged slowly, like frost on a window. This is the domain of prebiotic chemistry, the study of how life might have started when there was no life at all. And it is, in every way, a science of deep subtlety. There was no blueprint, only molecules. The early Earth, as far as we know, was not a sterile laboratory. It was messy, dynamic, violent, but it was also full of gradients, hot and cold, wet and dry, acid and base. These gradients are where complexity hides. They act like sieves. They filter and concentrate. They give certain reactions more energy than others. Somewhere in that soup of carbon, hydrogen, nitrogen, sulfur and phosphorus, the building blocks began to assemble. Let's look at what that means. One major area of research focuses on hydrothermal vents, underwater fissures in the seafloor, where geothermally heated water rich in minerals gushes into the ocean. These vents create steep chemical gradients, acid and alkaline waters, warmth, abundant hydrogen, catalytic surfaces like iron, sulfur minerals. This is where some scientists believe life may have begun, not in lightning-sparked puddles, but in dark, rocky chimneys beneath an ancient ocean. There's a beautiful simplicity to the idea that life began as a metabolic cycle, a loop, a set of chemical reactions that fed each other, driven by the gradients at the vent walls. Some reactions formed lipids, fatty acids that naturally self-assemble into membranes. Others formed short chains of amino acids. Still others began to concentrate carbon molecules into more reactive forms. This isn't life, not yet, but it's direction, a kind of chemical memory, a recursion. If some structures happen to persist longer than others, they had more time to interact, more time to copy themselves. Eventually, over countless failed generations, they became something we might recognize as proto-life. This theory is often called the metabolism-first model. It suggests that chemical cycles came before genetics, that the engine preceded the instructions. But there's another school of thought, the RNA world hypothesis. This theory proposes that before DNA and proteins, there existed a world where RNA did both jobs. It stored genetic information and it catalyzed chemical reactions. This is compelling because RNA is known to do both. In modern cells, RNA not only carries messages, it folds into enzymes called ribozymes. These can cut, splice, and copy themselves under the right conditions. Could ancient RNA have evolved in tide pools, or within mineral cavities, or under UV light in shallow lagoons? Experiments have shown that under plausible early Earth conditions, basic nucleotides, the building blocks of RNA, can form. They're finicky, but possible. The challenge is getting them to polymerize, to link into chains long enough to matter. Still, with clays, with cycles of wetting and drying, with a little luck, it's not out of reach. Then there are lipid world models which suggest membranes came first. Fatty acids formed by hydrothermal reactions or even delivered by meteorites can self-assemble into vesicles, tiny bubbles. These vesicles can trap molecules. Some even grow, divide, and selectively allow certain ions through. Put lipids, RNA, and metabolic cycles together, and you have the pieces of life. But life doesn't begin at a single moment. It begins across gradients of time and complexity, across trillions of experiments, across ages of trial and error. It's not a spark, it's a fog, thickening. The earliest life forms, if they could be called that, were likely anaerobic chemotrophs, microbes that fed on hydrogen, sulfur, or methane. No oxygen, no sunlight, just redox chemistry. Some of them may have lived near vents, others beneath the crust, others in warm puddles enriched by lightning or UV light. The truth is, Earth may have had many origins of life, and only one lineage survived. Or perhaps all lineages merged, in a grand fusion of molecular strategies. We don't know, but we search. Scientists today run experiments that simulate early Earth conditions. They spark gases with electricity. They recreate ancient oceans in test tubes. They drip ammonia into basalt dust and heat it with infrared lamps. And again they find that under the right conditions, complex molecules form. Not just amino acids, but sugars, nucleotides, fatty acids. It's not magic, it's chemistry. Even space-based chemistry supports this idea. Meteorites like the Murchison carbonaceous chondrite contain amino acids and nucleobases, the letters of life, formed in cold, dark clouds of interstellar dust. The building blocks are not rare, they are everywhere. Which brings us to the field of astrobiology, the study of life beyond Earth. Astrobiologists ask, if Earth's early conditions produced life, could similar conditions do the same elsewhere? We now know that Mars once had rivers, lakes, maybe even oceans. That Europa and Enceladus have subsurface oceans, heated by tidal flexing. That Titan has organic chemistry in its thick atmosphere. That exoplanets orbiting distant stars may sit in habitable zones, where water stays liquid and chemistry can run its long, slow game. When we study the Hadean, we are not just looking backward, we are looking outward. Because every insight about Earth's early atmosphere, its chemistry, its stability, every clue from Zircon, from isotope, from lava, gives us a better chance at recognizing habitability elsewhere. And just as Earth survived a violent beginning, we now look for planets that may have done the same. We scan for atmospheres rich in gases that don't belong. Oxygen, methane, ozone. We search for the spectral fingerprints of life. Not cities, not voices, just imbalance, just breath. Because that's what life is, a chemical pattern that resists equilibrium, that keeps pushing against decay, that says over and over, not yet. And Earth, during the Hadean, was that kind of world, not dead, not fully alive, but resisting stasis, learning, through chemistry, how to become something more. It would take billions of years to reach eyes, or thought, or language, but the path was already there. The gradients were in place, the cycles were spinning, the molecules were beginning to speak, and here we are, holding it all in our hands. We now have instruments that can read the isotopic signature of water on Mars, telescopes that can peer into the atmospheres of distant exoplanets, spacecraft that sample the plumes of Enceladus, rovers that roll across Martian lake beds, laboratories that recreate hydrothermal vent conditions from 4 billion years ago. And at every turn we see echoes, not of us, not yet, but of what we once were, a planet searching for balance, a molecule trying to persist, a cell dividing in the dark, a dream coalescing in rock and water. In the end, deep science isn't about reducing mystery, it's about learning to see mystery more clearly, to name the forces, to watch their patterns, to measure awe, not to shrink it, but to share it. And so we look, and test, and refine, not just to understand Earth, but to understand what a world can be. When the worst is over, the silence arrives first. Not peace, not clarity, just silence. A world exhausted from its own creation, from its fires and collisions and storms. The late heavy bombardment has waned. The magma oceans have hardened into crust. The haze begins to lift from the atmosphere. Rain falls, not in steam or acid, but in water that cools the land it touches. This is the moment when Earth pauses, not to rest, but to allow recovery, to allow time, to allow the next great chapter to unfold, not with violence, but with persistence. And in this long silence, something stirs. The Hadean Eon fades slowly into the Archean. There's no sharp line between them, just a change in rhythm. The chaos hasn't ended, but it's shifted. What begins now is the first sustained attempt at stability. And stability in a planet like ours is never passive. It's always earned. The oceans are now more than storms. They are systems. Currents circulate, minerals dissolve, salts accumulate. Silicates from the land drift into the sea, forming clays and sediments. This is the beginning of the sedimentary record, the first pages in Earth's physical diary. Meanwhile, deep beneath the sea, hydrothermal vents pulse with energy. They spew hydrogen, methane, metal ions. These aren't pollutants, they're ingredients. In the mineral crevices near the vents, ancient chemistry continues. Membranes form, catalysts align. Chains of carbon try again and again to organise, to remember, and somewhere in that matrix of trial and error replication happens. It may be nothing more than a strand of RNA, or a vesicle that divides unevenly, or a molecule that catalyses its own assembly, but it's enough. Life doesn't bloom, it doesn't leap into complexity, it persists. That's all it needs to do, just persist. The early biosphere, if we can even call it that, is invisible. No forests, no oxygen, just microbes, chemotrophs feeding on gases, anaerobes, extremophiles. The kinds of organisms we now find near volcanic vents, in salt lakes, deep underground. But these early microbes are doing something extraordinary. They're interacting with the planet itself. They're changing the atmosphere, the oceans, the rocks. They're starting to leave marks, carbon isotope signatures, faint traces in banded iron formations, slight shifts in the sulfur cycle. These aren't fossils, they're fingerprints. And they're some of the only evidence we have of life's first breath. It's a strange idea that the most enduring consequences of the Hadean might not be geological, but biological. That out of molten rock and storm-torn skies came chemistry precise enough to build inheritance, and that inheritance spreads. By 3.8 billion years ago, life may already be widespread, not diverse, not even very efficient, but resilient. Populations grow, mutate, shift, new enzymes evolve. Some cells learn to fix carbon, some to harvest light, others to eat sulfur. Slowly, a biosphere begins to knit itself together, one cell at a time, and with it comes consequence. Some of these microbes, likely cyanobacteria, begin to photosynthesize, not like modern plants, but using sunlight to split water and release oxygen. At first, this oxygen is a poison. It binds with iron in the oceans, forming rust-coloured bands that settle on the seafloor. These are the banded iron formations, the first grand monuments of biological activity. Eventually, the iron runs out. Oxygen has nowhere to go, so it builds. The Great Oxidation event around 2.4 billion years ago will flood the atmosphere with O2. It will end the Archean. It will trigger ice ages. It will alter mineralogy, metabolism, evolution itself. But even now, long before that tipping point, the stage is being set. This is how Earth recovers, not by going back to what it was, but by becoming something entirely new. And the consequences are long. Plate tectonics continues, recycling crust, shifting continents. The mantle cools slowly, reducing volcanism. The magnetic field strengthens, shielding life from solar radiation. The atmosphere thickens with nitrogen. The oceans stabilise in salinity and temperature, and life, for the first time, begins to shape its own environment. Microbial mats form on shallow seafloors, called stromatolites. These mats trap sediment, build layered structures, alter the chemistry around them. They are colonies, precursors to ecosystems. Some still exist today in remote lagoons, living fossils of a time when microbes ruled the planet. These early forms of life don't know what they're doing, but their presence changes the future. Because when you exhale oxygen for 1 billion years, the world adapts. When you modify the carbon cycle, the planet responds. When you die and fall to the ocean floor, you seed new chemistry. There is no separation between Earth and life anymore. They are one system now, entangled. Every geologic process is influenced by biology. Every biological process shaped by geology. Sedimentation, oxygenation, carbon sequestration, weathering, sulfur cycles. They're not just planetary processes, they're feedback loops. A single cell doesn't seem like much, but multiply it across oceans, across eons, and it becomes a force, and that force leaves marks. Rocks that wouldn't form without microbes, minerals that only crystallize in the presence of life, isotopic signatures that betray the hidden hand of metabolism. These are the long-term consequences of the Hadean. That Earth became not just a place where life could exist, but where life could intervene. And this partnership, once formed, becomes permanent. When mass extinctions come, and they will, the biosphere collapses, but the Earth remains. When oxygen poisons the atmosphere, organisms adapt. When glaciers cover the world, microbes survive beneath the ice. Because the story of recovery isn't about speed, it's about continuity. There are no winners or losers, no climaxes, only lineage, only life learning to persist. And so the Earth, this once molten orb, becomes a collaborator. It offers minerals, energy gradients, climate stability, tides, moonlight, and life responds by diversifying, by inventing photosynthesis, fermentation, respiration, by evolving membranes, motility, symbiosis, by building the complexity that will one day become plants, animals, consciousness. All of that begins here, in this long recovery, in this quiet transformation, in this space after fire. It's tempting to think of the Hadean as violent and the Archean as gentle, but it's not quite true. The Archean is full of struggle. Mutations fail, ecosystems collapse, climate shifts, extinction shadows everything. But compared to what came before, it's calm. And in that calm, something precious is allowed to form. History. For the first time, the planet has a memory not just of chemistry, but of biology. The carbon cycle now has a biological signature. The sediments record ecological succession. The atmosphere tells us about metabolism. Earth becomes not just a witness to life, but its author. And every era since has echoed that pattern. Extinction, recovery, adaptation, feedback, resilience. The long arc of consequence that begins when fire gives way to water and water gives way to breath. Today, we live at the distant end of that arc. We carry the consequences of the Hadean in our bones, in the oxygen we breathe, in the energy we burn, in the DNA that still remembers its origin in a lipid bubble, in a hydrothermal vent, in a world long gone. And if we listen closely, we can still hear it, in the rust of old iron, in the salt of the ocean, in the slow, patient drift of continents. This is the Earth recovering, not quickly, not completely, but enough. Enough to try again, enough to become what it was never designed to be. Alive. There's something strange about knowing how the world began. Not just the stories of myth, not the fire gods or the turtlebacks or the primordial chaos, but the real story. The one written in isotopes, in zircon, in heat and silence and slow accumulation. It's not a story we were meant to know, not really. The Earth didn't leave us a welcome note or a time capsule. It didn't intend to be remembered. And yet here we are, piecing together its earliest hours by moonlight and microscope, deciphering 4 billion years of transformation from the curve of a rock or the oxygen locked in a crystal, and knowing it changes things. Because once you've seen how much the Earth has survived, how it recovered from bombardment, from boiling skies, from cataclysm, you begin to realize how delicate it all still is. This planet is ancient, yes, but also young, not in age, but in stability. Life has only had a few moments of relative calm, and we are living in one of them, a moment where continents don't rearrange too quickly, where the oceans stay liquid, where oxygen holds steady, where sunlight arrives on time and tides rise in rhythm, where Earth's long, unstable adolescence gave way, just barely, to something habitable. And in that habitable span, we arrived. Not as inevitability, not as climax, just as possibility, just as one more form in a long line of trials. And here's the strange part. We too are forces now. We are not passengers on this world. We are participants. We burn fossil carbon and release it back to the skies. We farm, we mine, we dam rivers. We've lit up the nights with satellites, carved mountaintops into highways, changed the chemistry of rain. The carbon we're releasing is ancient, buried during other planetary upheavals, Permian forests, Cretaceous plankton, all stored away, compacted under heat and time, only to be returned in a geological instant. And that return matters, because Earth is sensitive. It balances between feedback loops, ice and water, carbon and rock, sunlight and albedo. A small push here can echo for millennia. A temperature shift today can shape ecosystems for ages. We've seen it before. When oxygen first rose from microbial breath, it froze the world. When volcanic CO2 surged, it turned oceans into deserts. When impactors struck, they erased species like brushstrokes. We are not the first to cause change, but we are the first to understand it, to know, deeply, scientifically, irrefutably, that what we do reverberates, that the Earth is not a passive stage but a living system, that the biosphere isn't just scenery, it's scaffolding, that coral reefs are climate regulators, that forests are oxygen recyclers, that peat bogs are carbon vaults, and still we act as if we're separate, as if geology is backdrop and we are the scene. But we are not outside Earth's history, we are its latest chapter. Every breath we take is filtered by cyanobacteria's descendants. Every metal in our phones was smelted in Earth's molten adolescence. The calcium in our bones, the iron in our blood, the salt on our tongues, they're all pieces of the planet's deep memory. We are not aliens here, we are not intruders, we are Earth, thinking about itself, briefly, fragilely, miraculously. And that thought comes with responsibility, because now we know how it all began. We know how rare it is for a planet to stabilise, how unlikely it is to hold on to oceans, how precious it is to have plate tectonics, a magnetic field, a steady sun. We know that life, once begun, can be nearly impossible to extinguish, and yet terrifyingly easy to disrupt. We know the signs of collapse. We can read them in the rock record. Sudden changes in isotopes, in fossil layers, in trace metals, spikes of methane, bursts of sulfur, gaps where diversity once bloomed. We know what it looks like when a biosphere gets pushed too far. And now we can see echoes of those signals today. Rising CO2, melting permafrost, shifting rainfall, bleaching reefs, vanishing insects. The planet has been here before, but not with us in the story, and this time we have a choice. Because the same tools that revealed Earth's ancient past, the microscopes, the models, the satellites, the sensors, also show us our future. They let us see the curve before the drop, the inflection before the feedback loop kicks in. They give us time, not forever, but enough. Enough to steer, enough to remember that catastrophe is not the end. That Earth has recovered before, not quickly, not without loss, but with resilience. That even in the Hadean, after the sky fell and fire ruled the seas, there was still a future waiting. Recovery is not a miracle, it's a pattern. It's photosynthesis rebounding after acid rain. It's coral larvae finding refuge in new waters. It's a single grass blade pushing through scorched soil. But recovery only happens if there's space for it, if we leave room, if we recognise that the systems we depend on, air, water, weather, soil, are not fixed, that they are dynamic, responsive, living, and that we too must adapt. It's not about returning to a natural world. Earth has never stood still. It's about learning to move with it, to synchronise, to become stewards of feedback, not masters of extraction. To remember that the planet doesn't need saving, but we might, because the Earth will outlast us one way or another. It has already survived worse. But if we want to be part of its next chapter, If we want to belong to the long memory of this place, we need to live like we remember how it began, with humility, with awe, with patience, not because Earth is fragile, but because we are, and yet there is hope in that fragility. Because for all our mistakes, we have also done something no other species has. We have listened. We have reconstructed worlds we never saw. We have mapped continents that no longer exist. We have dated raindrops that fell 4 billion years ago. We have built an archive of memory far deeper than our own experience. We have, in our quietest moments, asked, where did we come from? What does it mean to belong to a world like this? What might come next? And Earth has answered, not in words, but in stone, in chemistry, in rhythm. And perhaps that is the most important parallel of all, that the past is not a warning, it's a guide, a record of what is possible, a testament to change, to chaos, to survival, and to the quiet, persistent beauty of a world that refused to give up. Not after fire, not after ice, not after impact or oxidation or extinction, not after us. So wherever you are, whether you're lying in the dark or walking under starlight or drifting slowly into sleep, know this. You are a part of something ancient, something enduring. You carry in you the breath of bacteria, the heat of magma, the dust of stars. You are Earth's consequence, its experiment, its story still unfolding. And somewhere deep beneath your feet, the mantle still turns, the Zircon still count, the oceans still dream of lightning, and the planet, your planet, is still becoming. And so here we are, at the edge of the beginning. We've travelled back through deep time, through magma oceans, stardust, storms and silence, to a world unrecognisable, and yet still ours. A world that was not built for life, but became its home. A world that cooled, cracked, breathed and softened until it could carry oceans, bear life and hold memory. We've traced the recovery, the resilience, the persistence of molecules that learn to endure. We've followed the clues left in crystal lattices and isotope ratios, in ancient zircons and whispering vents. We've listened to the Earth, and in doing so, maybe heard ourselves. This story was never really about rocks. It was about time, and patience, and wonder, and the quiet, staggering beauty of a planet that made room for breath. If you've made it all the way here, thank you. Whether your eyes are already closed or still wandering gently across the ceiling, I hope this journey offered you a kind of stillness. If it brought you peace, or sparked a thought, or simply kept you company as the hours slipped by, I'd be honoured if you left a like, or subscribed, or shared this little space with someone else who needs a soft place to land. And if you're still listening, or drifting, let me ask you this. What else might Earth remember? What other chapters lie buried in the rock, waiting to be read? Next time, we'll follow another of those ancient threads, perhaps the day life learned to breathe oxygen, or the moment continents danced across the globe, or the strange frozen world of the Cryogenian when glaciers reach the equator. Because the story of Earth isn't over, it's just getting started. Until then, sleep well, stay curious, and remember, you're not just on Earth, you are of it. Good night